Thank
you. Yeah, but yeah. Yes. Now I can't see anything. Great. Why is it disabled? Who knows? My own screen was disabled. Anyway. No, it's still not working, just synced. Okay. Okay, I think this is okay. Right. Something's wrong. It's not my, or my, whatever. Something is wrong. I mean, I can't switch between my tasks. This Alt tab doesn't work anymore.
Or maybe it does, but it doesn't show it.
Yes, but why?
No idea. But if you
But
stick between just two.
Yeah, but where's my Visual Studio now? This is sorry. I think I just restart my machine. Or
Maybe if you. I know.
I think I just.
Yeah, sure. And disconnect is just.
Just a second. There's some trouble. There it is. Now it's there. Great. We'll get there. Okay, this works again. Okay, so now my machine at least works again. Okay, now let's do this again. Okay. Okay. No, not okay.
For some reason this menu gives.
Yeah, but I think that disappears automatically after a while.
Okay, I will wait 5 minutes. There you go.
Okay, so hopefully it works now. Right. So today I hope is a fun lecture because it's more of a demo of the stuff we have learned in the last days, especially yesterday. So we saw this simple server and we talked about concurrency, and today we will bring the two together because, so we will talk about servers again. I mentioned MVARs yesterday already, so we'll repeat that. And then we will talk about servers with state. I mean, the point of this shouting server, I mean, that was particularly simple because the clients were completely independent of each other. So they didn't need to communicate or know anything of each other. Of course, with a realistic server, normally you have state, for example, a database. So we'll do that today. Have a bit more of async and STM. Talk about channels. And then have a demo of implementing a chat server where, I mean, people can chat with each other and send each other private messages and so on. And this is closely following a book by Simon Marlowe, Parallel and Concurrent Programming in Haskell. And right. So let's look at the shouting server again. And I just Right, and before I proceed, I just want to make it a bit nicer. So I have the code from yesterday. Just a second. So I think this is just copied the code from yesterday, except for this, so it passes. Right. So the very first thing I want to do is I want to move that into a library, because normally, I mean, for a simple example like that, it's okay. But normally, if you have like an executable, you have most of your code in a library in the Cabal package, and the executable only calls like a library function and has very, very little code. So let me do that. I already prepared a source folder here, and there is a shouting module, but at the moment it's completely empty. So let me just copy this, everything maybe, into this module. And then I shouldn't call it main. So let me call it run, for example. And I export it here in the module. Okay. And here now I just call run. And then I don't need any of these imports anymore. but I do need to import my library, which I called servers. I mean, it's servers shouting in this case. Right. So let me see. Okay, something I made wrong. I made a mistake. Right. I must update the Cabal file. I haven't done that yet because I really wanted to start from where we finished yesterday.
No.
Yeah. So now in the Cabal file, I don't need these dependencies anymore because this is now in the library. But I do need now to actually reference the library, which I called servers. So here's the library. So I already prepared for later today these modules, but at the moment they're all empty. These server.chat, counting, shouting utils. And I just copied the code from the executable into shouting. So this should hopefully work now. Okay, let me just reload here as well. So it didn't do much. I just moved it into the library. Okay, so that was the first step. And now I want to refactor a little bit. Okay, let's first try whether it still works. So Cabal run shouting server. So listening, and let me switch to my local machine, make it larger for you. Npcap. So that still works. And if I Control C, then we get this error here. So the first thing I want to do is, I mean, that's not nice that we don't handle this error. So I want to write a safer version of hgetLine. And for that, I also, because I will use that in the other examples of today as well, I created a module utils for this that I can then reference from all the ones. So let's call it, or let's call it getLine prime. So it takes a handle, and let's say I have a choice now. No, let me just think. No, I want to do that differently, sorry. The other thing, I want to do that, sorry. But the other thing we do is we get this socket here, as I explained yesterday. So it's socket-based, this network simple, but then we create a handle from that, and then we work with the handle. And then when we read from the handle, if the connection is closed, we get this error. So I want to abstract this away because I will need that everywhere. So I will define something that I call with socket. And the idea is I get a socket. And then if I have something that knows how to write a line and read a line, then I can build an application from that. So let me do this. So writing a line should be something of type string to IO, but this gets like messy, so let me define a type for that. So write line is string to IO, and read line is IO string. So these are the types of put string line and of get line, right? As you recall. So what I want to do now is I want to get rid of, I don't want to, for each example, do this socket to handle thing. So I wanted to call that write line. Write line, read line, IO. Then I want to turn that into something IO. Okay, now must import this. And of course I must implement it. Okay, socket. handler. Let's call it handler. So basically it's the type, it's the code from here, a part of it. So let me just copy this line here. So I want to use handles. Now I must import, of course, all the stuff, which for some reason I can't. I think it's because it's syntax error. Just 1 second, let me get rid of that. Okay, now it's called socket. I need to import this from system IO. Okay, so first line is what we did. I mean, we have the socket and we turn it into a handle in read-write mode. So now given that, I could now call my handler and I must now define this write line and read line. So how do I write now? Well, now that I have the handle, I can do h put string line h and h get line h. And I must import those as well. So I mean, this would compile, so this is correct. But of course it doesn't, I mean, this is a pure refactoring. So actually it doesn't change anything. But I can already use that. Let me do write line, read line with socket. And now let's refactor this to use these things. So here, first of all, this handle client, it uses the handle, but now I want to write it into, I mean, abstractly use this write line and read line. So abstract away from the handle. And let's call it write line and read line. Okay, this I will also put into this helper function here. Because I always have to do that. So I don't need that in my handlers anymore. And now instead of this, I use my, I called it read line. And instead of the h put string line, I now can use my write line. Okay, and now here, this I don't need anymore, so now I can do with socket prime, handle client. Okay, so this should be a pure refactoring. That doesn't change anything. So, I mean, we can try it again, whether it still works, but it should have the same problem with this unhandled exception. Okay. Let me see. Yes, so this is a pure refactoring. I've just turned this, I mean, now to get a handle from the socket, and then once we have the handle, how to write to it and how to read from it, I've just moved that into this helper function with socket. And actually, this is a common pattern in Haskell. I mean, and they are normally called with. That I mean, we saw that once with file. We saw this function with file from system IO, where you give a file name and a IO mode, how you want to open the file, read mode, write mode, and so on. And then given a function that using a handle gives you something, let's say, I mean, kappa REPL, import system IO. This was, we talked about this. So this is similar. So you open a file and then I give it IO mode, and then given basically a continuation that can use a handle. If you with the handle can produce an IOR, then this whole thing produces an IOR. And then internally the implementation of the function will open this file, get the handle from after opening it, and then pass it to the continuation. And I basically now doing the same thing, which allows me in my handler to to work on a higher level, because now I don't have to worry about handles anymore. I can just use this write line and read line. So far so good, but as I said, it doesn't solve the problem. So what I can now do is just wrap, in the utils. For example, I can just wrap this whole thing into, I can catch IO exceptions in this whole thing. So here, for example. And we had that was catch, when we talked about IO, we had this catch IO error function. And it has two arguments. First, what I want to do, and then what I want to do in case of an error. Maybe I should write it inline in this case. Catch IO error. And now the handler takes an exception, an IO exception, and tells me what to do. And in this case, I can keep it simple and just constantly don't do anything and just exit. Now why is this? Okay, sounds good. Let's do this. Okay, fine. If I can write this, sorry. Maybe like this. Okay, so that means I will do what I did before, but if there's an IO error, then I will catch it and I will just, I won't write a message or anything, I just stop execution. Maybe not a good idea, but in this case I think it's okay. Right, and if I now do this, and let me run this thing again. Let me stop, there's still some warning it seems. Where was that? Sorry. Not there, here I suppose. Oh yeah, because now I have refactored lots of stuff into the library, this also becomes much simpler. Okay, let's do this again. Okay, now there is no error anymore. One other thing I maybe can do is maybe quite nice. I say this accepted client, so maybe afterwards I can just say client disconnected. This should now be fine. Earlier this crashed, so it would never have reached this line when the client disconnected. But now we should actually get there. Okay, let's try this. Yes, so okay, that's good. And there's one final, or two things. Sorry, do you have a question?
Before you continue, you could change this clear function that Lars used to, for example, log the errors in some other server or something like that to keep track of errors or whatever happens. So it's just to keep going so it doesn't crash and keeps going. But you could use that IO, you could do any IO action. You can save things to the database, log errors.
Right. Now I want to do one refactoring. We use this accept fork, and I told you yesterday what it does is it accepts a client connection and then forks the handling of it in a new thread. But now I want to do that explicitly. There's also accept with the same signature, which doesn't handle the client in a new thread. But I do want it in a new thread. I just want to split this into commands. So now I put my fork IO here. Or actually I can put it, yeah, let's put it here. I'm not sure. It might be that then that sometimes the output is garbled.
Behind the accept.
Yes. Here? Behind here?
No, the accept. But you want to refactor all that out?
Yes.
Yeah. Yeah, you can put it there in the first line.
Yeah. So this is always on the main thread, the accepted?
Yeah.
Oh, okay. Right. So I put it here. Must import control concurrent as we learned yesterday. So this is more or less exactly the same now as before. So, but instead of using this higher level accept fork, I now do that explicitly. So I accept and then explicitly fork the handling on a new thread. That should still not change anything, and I should still be able to connect several clients simultaneously. So let's try that. So I do it here. First. And I open a new tab on my machine. It always takes a while for some reason. Okay. And switch back and crash here or disconnect and here as well, and now look, and hopefully, yes, so we have both of them. So it's as before, and it is still able to handle like several clients at once. Okay, and now the reason I wanted to do this, that I move this in, split that, is because now I want to replace fork IO as we saw yesterday. If you don't do anything, it will just, the main thread won't be affected by it. The main thread doesn't know when it stops or whether it crashes or whatever. But there is a variation on fork IO, which is called fork finally. And we can open a REPL again, import control concurrent, and ask for the type. So this gets an IO action. That's as before, as for fork IO. So it will, execute that action in a new thread. But it will also get an exception handler. But it's not, okay. So it's like, probably you know that from Java or whatever. So, there's often this try, catch, finally. So that's that basically, without the, so it will always run a finalizer in the end. So the second line is what it will always run in the end. And there are two cases. Either the IOA action succeeded, then this finalizer will get as an argument write the result, or there was an exception, in which case it will get left the exception. But no matter what, this thing will be executed. And I want to be able to execute something after, on the main thread, after the fork has died, the thread has died. So I want to use that. And now, of course, now I can basically do this as my IOA. And I can do this as, I don't care whether it succeeded or not. Why does this not work? Yes, right. So in my case, it probably won't be an exception. It will always succeed, but it doesn't matter. It just means the client has disconnected, and so I just want to do this. So that should still behave exactly the same as before. But later in later examples, in the next example, we will then do more stuff here. So that's why I wanted to split it like that. So again, so what will this do? Once a client connects, it will accept the connection and then fork a new thread where it will execute this, which will just handle the client. And once this has finished, and it doesn't matter whether it finished normally or with an exception, this here will be executed. So hopefully that works. Oh, let me just, there was some warning. Okay, because now I don't need this anymore. Okay, so that's also nice, it gets simpler. Or at least not more complicated. Okay. We do my 2 again. And it still neatly works. So this is right. And I think now it's in a form where we can go to the next example. Are there any questions at this point? Okay, so it's basically our shouting server from yesterday. I made it by catching the error if the client disconnects. I get rid of this annoying error message. And I now have more control. So now the main thread gets a chance to do something when a client disconnects. So it basically gets notified. So this finalizer runs. Okay, so if there's no question, then let me just copy this. So the next example I called counting, and at the moment counting is empty. So let me just copy what I have in shouting now to counting. Copy source shouting, server shouting, source server counting. And now, of course, I must change the module name back to counting. And let me copy app shouting server to app counting server. And in counting server, all I have to do is, I now don't want the run from shouting, I want the run from counting. At the moment, of course, it's identical. But I now want to continue, change this run from the counting for our next example. Okay. Right. Okay, so in this shouting server, as I said before, I mean, the clients are completely independent of each other. So there's no state needed in the server. And of course, it gets more interesting if we add state. And as a very simple example, the state we want to, I mean, it's just an example for state and it's not very useful, but the state we want to use as an example is the number of connected clients. So the server should be aware how many clients are connected and tell the clients, or the clients can ask for it. So instead of shouting, it will now tell the clients how many clients are connected. So there's shared state. The server knows how many clients are connected at the moment. And we have several options to maintain that state, as we discussed yesterday. So for example, we could use a TVAR. We could use an MVAR. I'll say a bit more about MVARs in a second, basically just a repetition of what I said yesterday. Or we could use an IO-ref if we are careful and only update it atomically. And in this simple case, because it's just one int, the number of connected people, that would all be okay, and IO-ref would also be okay. If the state is more complicated and you have to keep several things in sync, then TVAR is probably the best choice. And just, I think I said that basically verbally yesterday already. This is just to work with MVARs, because I think in the exercises there is at least one exercise to use MVARs. And I did explain that before already. So I think of an MVAR like a box that can contain A or it can be empty. And it has two, I mean, you can create it and you can create it both. I think that's on the next slide. Right. There are two ways to create an MVAR. You can create it empty or with a value inside. So the new empty MVAR creates an empty box, and the new MVAR takes an A and then creates a box with that A inside. Right, so that's how you create one. And then it has two fundamental operations. Put, to put a new A into the box, and take the A out of the box. And the behavior is as follows, as it says there. So put, if the box is empty, it will put the A in and immediately continue. But if the box is full, it will block the thread that tries to put until some other thread takes the A out that's in there now, and then it will put it in. And take MVAR is like the dual case. So if the box is empty, it will block and wait until somebody puts some A in and then take it out. And if it's full, then it will take it out immediately and empty the box. And it can be used in several different ways. I mean, as synchronized mutable variables. You can use it as a channel. So if I want to talk to a different thread, if I want to send a message, I mean, it can then be an MVAR of string, say. So if I want to send a message, I do put MVAR, and I block until, I mean, if, let's say it's empty in the beginning, so I put MVAR, and the other thread waits for messages, and it blocks until the message is there, and it can take it out. And then I can put the next one in. And you can also, I also mentioned that yesterday, if you use MVAR unit, so the value itself is not interesting, so it's just interesting whether the box is empty or full, but there's no interesting value in it, then you can use it as a binary semaphore. So as a lock, basically, as a classical lock. So if you have a critical section that you only want one thread to execute, to entry into, I mean, with one time, then you can create an MVAR unit, and then whoever wants to enter this block takes it. So if nobody else is in there, you can take it. And when you're done, you put it back. And so no two threads can enter it because somebody, I mean, the one in there has it, and the others have to wait until he puts it back. And of course, the usual problems, I mean, if you crash before putting it back, then everything is deadlocked. Right. And MVARs offer more flexibility than IO refs, but less than TVARs. And you can build synchronization primitives and do some inter-thread communication. But as I already mentioned yesterday, they are susceptible to race conditions, deadlocks, uncaught exceptions. What I just said, if you hold a lock and then crash, then everybody else blocks forever. So if you do more complicated thing, then TVARs are probably the best choice, and you should use them. And incidentally, the Cardano node, for example, uses TVARs excessively all over the place. I mean, you don't need, normally if you do Plutos and DApps, you don't need TVARs, but I mean, if you are interested in actually developing like Cardano itself, then TVARs are very important. And there is one advantage of MVARs over TVARs. That's, I think I mentioned that, I'm not sure. There's this fairness guarantee. So there's a guarantee that's in the specification of MVARs that no thread can be blocked indefinitely on MVAR unless another thread holds that MVAR indefinitely. So if several threads want to take an MVAR, then, and if like always somebody puts it in, then at some point the thread will actually get it. So it can't be that, I mean, there are 3 threads waiting, and only the other 2 always get it, but I never get it. And so that's a guarantee that can be implemented first in, first out. So basically the people waiting for the lock are in a queue, and then the first one gets it. I mean, that would ensure this, but it's not guaranteed that it works like that. But it is guaranteed that, I mean, the first statement. And that is not the case in TVARs. This guarantee is not there. And okay, that's just basically the API for MVARs. So the first 2 to create. Put and take we talked about. Read is like take, but take takes it out once it gets, I mean, once there is something and it takes turn to take, then it takes it out and leaves an empty MVAR. Whereas read also blocks if it's empty, but then if somebody fills it, it just returns the value in there but leaves it in the box. And then there are also try versions. So these 3 here can block. I mean, put blocks if the MVAR is full, and take and read block if it's empty. And the try versions, if the non-try versions wouldn't block, they behave the same. but if these would block, then they don't block and instead return nothing, or false in this case. So for example, try put mvar, if the box is empty, it puts it in and returns true. But if the box is full, it doesn't block and wait until somebody empties it, it immediately returns with false. And similar for try take and try read. And finally, modify and with is similar to what we saw with IORef. So for example, modify will wait, block if it's empty, and once it's full, it will basically look at the value in there and then put the result, execute this IO action and put the result here back into the box and return the B atomically. So nobody can interfere with that in the meantime. And I think, and with mvar similar, so it will block until the mvar is full, and then once there is an A, it will use that A to perform this action, and in the meantime, nobody else can get to it. So that actually can be used nicely for logs. I think there's also an exercise for that, like one of the exercises for concurrency. Okay, but this is nice, but we won't use it today. So we instead use a TIVA. Yes? Okay.
Concerning mvar, what does it mean that fairness warrant is not given in semantics?
That fairness what?
The fairness warranty is not enforced in the semantics.
Let me go back. No, it is guaranteed. The first statement is guaranteed in the semantics. It won't block indefinitely, provided no other thread holds it indefinitely. That is guaranteed. What is not guaranteed is that this is implemented by releasing locks in the first in, first out fashion. So you could implement this guarantee of the first point by creating a queue. So everybody that waits for that mvar is in a queue, and first in, first out. So the first in the queue gets it first, and then the next in the queue, and so on. That would guarantee the first point. But the statement just says that it's not guaranteed to be implemented in this first in, first out fashion. It could be implemented in a different way, as long as that different way still guarantees the guarantee. That's what it means. And probably GHG does implement it like this, but I'm not sure. Was there another question? Okay. Right. So one way to do this now. So we use a TIVA. Okay, let's just do it. So now I go back to counting. One more thing. In the executable, no, I already have that, sorry. All good. I already removed this. Right. Okay, so in the counting, so we need this, we need global state now to count how many are connected. And let's use TIVAs. So here, before I start listening, I just initialize this. And let's call it whatever. What is it called on the slides? Cons for connections. So new TIVA IO 0. So in the beginning, nobody is connected. And it's complaining because it doesn't know whether the 0 is, whether it's an int or an integer or whatever. But that will go away, because now I will, in this handle client, I will pass in this TIVA int. Import this. Right. So far so good. So it compiles again, but doesn't do anything at the moment. So now, of course, I must somehow increment this each time somebody connects. So in handle client, I just increment this variable. Okay, so atomically, was it write Tiva? Yes, write Tiva cons. No, modify, sorry. Modify Tiva prime. Okay, import stuff. Okay, so now I increment it each time somebody connects. Like we learned yesterday with this atomically and modify Tiva prime. I should also decrement it again when somebody disconnects. So this is now handy that I have this finalizer here. So let's do this here. What's the problem now? Okay. Sorry. Okay, and finally, okay, so this should now, it should now have the correct value all the time, but it's unobservable at the moment. And in this first example, we don't do the shouting anymore. We don't care what the client says, and we just return, so we just read, so let's call it N or X. Oh, there is a read Tiva IO, so I can do that shorter. Okay. Just see this. Okay, I don't need this shout stuff anymore. Okay, let's see whether it works. So now counting server. Okay, listening. Let's connect the first one. Okay, nothing happens, but now the way it's implemented, each time I press enter or a line, I should get the currently connected clients. So I get a 1 because I'm the only one that's connected. So now let's do this and press enter here. So now it says 2, and if I switch back to the other one, it also says 2. And if I now disconnect this one and go back here, it's back to 1. So it seems to work. I mean, of course, no proof, but so now we have state, shared state. So the server keeps track of how many connections we have, and it can tell, or the clients can ask for it. Are there any questions at this point? Okay. Right, let me just check the slides. So I think, I mean, this I already told you in the beginning. This we did. Right? Did it like this, more or less? Okay, and now we want to make that a bit nicer so that the clients don't have to ask for the number of currently connected, but that the server tells everyone. So each time it changes, each time there's a change in the number of connections, connected clients, each client should be informed. So the server tells them without having to ask. And one option is that instead of just having a number that tells how many are connected, we change the type of our Tiva, and we remember handles. And that is now a bit silly. I wonder whether I can actually do that with my abstraction now. Because I don't have the handle anymore. Maybe with the socket. I didn't think about that. Let's see. Maybe. I mean, I could do this write thing. I mean, the writers instead of the handles. Maybe that works.
Yes, but we have to pack and unpack.
Pack and unpack?
Oh no, so yeah.
No, I think. So I diverged a bit from the slides because of this. I mean, I need to be able to talk to the clients. And I do that with my write line, which was wrapping the handler and doing this hput string line on the handler. In the slides, I now want to remember the handlers, but instead I think I will remember the write lines. So how would I do that? So instead of new tvar, I mean, instead of 0, so now this is supposed to be a list of ways to talk to the clients. It starts empty, of course. So instead of tvar int here, I have now a tvar write line. So a list of write lines. So let's see. Why is this? Hey, just a second. There's weird formatting. Something went wrong there earlier, I think. No, but this client disconnected, that's somehow duplicated. So at some point, I must have messed up somewhere. Hang on just a second.
Okay.
This is still correct, right?
Yes.
So, no. Okay. Okay, so I changed this into tvar list of write lines. Okay, and now instead of adding it, instead of adding one, I must put my own write line top of this list. So this is now write line colon. Okay, and here I don't do anything anymore. I just forever do a read line and ignore the result. Oh yeah, that's not legal, so I must use void. Okay. So that doesn't do anything anymore. I mean, the client can type whatever it wants, doesn't matter. So now somebody, of course, one thing here, when I remove, so what do I have to do now? Now I'm in trouble, right? Because I can't. Because I don't have the write line. So that's not going to work like this.
You have to get the list like cons 1? Or
I'm sorry?
you have to get the list from the main thread in cons 1?
Some of the socket, I must use the socket. Just 1 second, excuse me. Sorry, I just want to see the socket type. Socket. Okay, there is econ socket. If I somehow save the socket as well, then I can. Right. I probably should have thought about that a bit better. So the problem now is how do I remove this again? And I don't have that at this point because the write line is only available inside here. So I need something like an identifier of the connection. So I think I instead will do a pair of a socket and how to write to it. So instead of just this, I do socket write line. Let me just must import this. Okay. Okay. Now, of course, this thing doesn't know its socket, so I need to pass it in as well. It's a bit unfortunate, but never mind. So I const the pair of the socket. And this. So this is now correct again. And here I must just also pass in the socket. So this is now also correct. And now I can implement that, remove it again. So I just filter the list. And if I have a list element with S, then S must not be socket prime. So far, so good. So I think now everything compiles again. We need that now. Right. But now, of course, because I remove, earlier it was that if the client presses enter or enters a line, then it gets the number of connected clients. But now it won't, because, I removed this code. So now the idea is that the server tells. But at the moment there is nothing that does this telling. So what we will do is we will have an extra thread that monitors this TIVA, and each time the length changes, it will notify everyone about the new length. Okay, so we will fork something we call monitor, and let me just check on the slides quickly to not diverge too much from the slides. So, okay. So in the beginning there are 0 connections and cons, and now we will implement this monitor. So monitor takes the current number of connections and our TIVA that holds these connections. And will just be IO. What to call it? Count cons. Right. So the idea is that here we will basically use software transactional memory to check whether the connections have changed so that the count has changed. So either somebody is disconnected or has connected. And if that happens, and otherwise we block. So, and we will return the, what will we return? Okay, handles a new count. Let me call it writers and new count. Atomically do. Okay. So what do? We read and if the length of, if we have as many connections as we had before, count, then we just retry. So this will block if nothing has changed. And else we will, sorry, it's fine, but I just wanted to give it a name. New count, length XS. So if new count is old count, then we don't do anything, we block, we wait until something changes, and else we return the writers. and the new count. And why, okay. Okay. Right, retryer must import. Okay, so again, I mean, this will, it gets the current count and the TIVA holding the connections. So now it will read the current state of, I mean, the current connections, get their length, and compare it to the previous count or the current count. So if it's the same, that means nothing has changed. Nobody has connected or disconnected. Or it has been happened, at least the number didn't change. In that case, we retry. So as we learned yesterday, this will just, I mean, it won't heat up the CPU. It will just block the thread until something has changed with the connections. So and if that's the case, I'm not interested in the sockets. I only needed them to be able to remove again afterwards. I'm only interested in the write lines because I need a way to communicate with my clients. So I return then, or the result is this pure pair where I just look at the write lines. So now I have all the ways to talk to the clients and the new count. And now I do talk to the clients. So now for now this is maybe nice where we can use 4M. So I have these writers. Given one, I can write line, what do I say? Number of clients changed to, show new count. Must import this. Wrong button. And now I recursively continue monitoring, but now the count has changed, so now I use new count. Right, and hopefully this should work. I hope. I haven't tried that. Okay, it doesn't compile. See? Or fork IO because I, right, what is it complaining about now? Oh yeah, because I ignore the thread. Let's do void again to get rid of that. Now it should be fine, hopefully. There was still a warning.
An import.
Oh yeah, I don't, because now I'm in atomically blocked, so I can't use the IO version. Let's do this again. Okay. Now let's see what happens if I connect with my first client. So without me doing anything, the server told number of clients changed to 1. And now if I connect the second one, this one gets the message number of clients changed to 2. And if I now switch back to the first one, we see the message also happened there. And if I now disconnect this one and switch back to the first one, we see it also. And if I, okay. So we achieved this goal and no exceptions or anything. Right, but this is somewhat brittle because, I mean, between the time, for example, here in this monitor, in this monitor, between here and here, I mean, here I look up these writers, all the connected clients, and then I send all of them a message. And in principle, somebody could disconnect between line 45 and 46. And in that case, one of the writers I have here is no longer available, and then probably it would crash. And that's, so this monitor thread would crash. Of course, I could catch the exception. But I mean, it can get messy, and especially because now, another thing is that now different parts of the program have access to these writers. I mean, the monitor can write, but the handle client also has access to it. It doesn't use it at the moment, but if it would, then I might like have problems with garbled output, that both the monitor and the client handler at the same time try to write a message. And therefore, doing it like this is not ideal. And I think we should have a short break. And then after the break, we talk about channels and how to do this better. And then we have like a final version of this, which will behave the same but be cleaner. And then finally today we can talk about a fun example, chat server. We will use this as basically the starting point. Are there any questions at the moment? Okay, then let's have a short break. I just wanted to, using Tmax, I can show like 4 different ones, and it's easier to demonstrate. I mean, I always had to switch between terminals, so we couldn't see what was happening in the other chat. So now I can. Let me run this once more, and let me just connect several times. No, I just wanted to try Tmax so that I can split my. So now you can see the client simultaneously. So you see that indeed the others at the same moment this one connects, get the messages. Okay, and if I now, for example, disconnect this one, then the others get the message at the right time. So yeah. Now they should all have crashed. Yeah, okay. I can just leave it like that, and then for previous, next examples also. Okay, so this works, and as I explained, it's a bit bad because something can go wrong with these writers and so on. So it would be better to have a better way to talk to all connected clients. And let's go back to the slides. So, could happen, it's a bit different on the slides because it uses the handles explicitly. So maybe I shouldn't have done this change, but it doesn't matter because with what we do next, this problem will go away anyway. Right, and I explained why it might be problematic. And the better solution is every client handler exclusively deals with communication with that client. Right now we had this monitor, and the monitor was talking to the clients. So it's better if the handlers talk to the clients. But of course the handlers somehow, they need to know about these messages that the server wants to send. And for that we have channels. So next we talk about channels. And that's something that can be built on top of, or we come to that, how it's implemented. So first, and the most important thing is basically that you understand the abstraction. I will later have a couple of slides about how to actually implement channels. But you don't worry if you don't understand that. It's not important as long as you know how to use this API. It's more fun exercise. So there is something called T-chain A. So it's a channel with A's. And the idea is you basically, a channel, you can write to a channel and read from a channel, and there can be like a given number of elements in the channel at any given moment. So somebody can write 3 things, and then somebody else can read one, and the first one can write again. And there are various flavors of channels in the libraries, also bounded channels, where if the channel has a certain number of elements in it, then it blocks on writing. But these ones are unbounded. So anyway, so you can, and it's in STM. There's also, I think, a version with MVAS, but we are using the ones in STM. And so you can create a new channel with new chain. You can create a new broadcast channel, which is a channel that you can only write to but not read from. We'll talk about why you would want to do that in a moment. You can duplicate a channel. So if basically there's a channel and it's already active and stuff is happening, and then you duplicate it, you won't get all the old elements from the channel, but from the moment you duplicate it, you will be able to read everything that's written into the original channel or the duplicated one from that moment on. You can read from a channel and write to a channel. So reading will block if the channel is empty, and writing will never block. So you can always write into the channel, and somebody can read, and if it's empty, it waits until somebody has written to it, and then you get the first element out. And only one thread will get an element. So it can only be read once, each element. So that's channel, and you can use that to communicate between threads. So if two threads share a channel, then one thread can write into it and another can read from it. So it can basically send messages between channels. And so did I say anything? So items written into a channel do not get lost. Items will be read in the order they have been written, first in, first out. I mean, as you would expect if you call a channel. And items can be read only once, even if accessed concurrently. So if two threads try to read from a channel and then a third one writes into it, then only one of the two will be able to get that element. And as I said, you can duplicate. That will create a new empty channel, but items written to the new or original channel will be available on both. And in this case, so an item can be read twice. So both on the duplicated one and the original one, you can read the same item. Okay. And okay, it's first using it. So let's do this. And then explain, then there will be a couple of slides explaining how actually channels are implemented using TVARs. So let's first use them. So now it gets simpler again. So now we go back to that our shared state is just the number of connected clients. So this was just an X curse with this list. So I change it back to 0. And let me do this first. So basically go back to the previous version. Hang on. So the client, this will now be again a tvar int, and I don't need the socket argument anymore. And this will become a simple, sorry, let's disconnect. So I don't need the socket anymore. It was a bit bad anyway. Why is this? Where is this right line thing still? Oh, because of this maybe. Okay, let me just change everything back to int. So handle client. Okay, and if a client disconnects, it's simple again now. It's just x to x minus 1. So this part should be okay again. So now handle client doesn't get the socket anymore. And the modification is now a simple +1 again.
We don't need the right line.
I'm sorry?
We didn't need the right line before.
No, okay, but anyway, now we will need it. Okay, so this now I just want the new count. So this also becomes much simpler. I just read this. I don't need this. And if C equals count, then retry, else pure C. This we will change. Let me just comment it for the time being. Just want to make it compile again, because that's annoying if it's not. So I think, okay, so far so good. So now we are back to before, but now nothing is happening. I mean, it updates the TVAR correctly, but there's no communication to the clients. And now we want to do that with a channel. So in the main program, I create a new channel, a new broadcast channel. I always forget what it's called. New broadcast T-chain. I/O I can use. Okay. And now these clients will also get the channel. And it could be int or string, that's up to me. Who creates the message? Let's call it, I don't know, doesn't matter, int. Okay, so this now also gets the channel. So the idea is this monitor will write into the channel whenever the count has changed, and the clients will read from the channel, and if there is something, then they will tell the client. So the handle client will read from this channel. In order to do this, they first have to duplicate it, because as I said, this is a broadcast channel, and you can't read from a broadcast channel. So in order to do this, we have to duplicate it. And this is an STM, so I do have to atomically. Okay. And now there's one more thing. I now want to, I think this is here already. Let me just check that I'm not too, right. Now I want to do two things. On the one hand, I want to read messages from the client and ignore them, but I just want to keep reading. And on the other hand, I want to also be able to write, so I want to do both simultaneously. And I do that with raise, which we looked at yesterday, which is from the async package. Just see how it's done here. Right, raise output. Okay. So I will change this, and I do void input raise output, and output will get this channel. And input and output, of course, I have to define. Later. Just want to make it compile, so I must import this. Okay, so far so good. Now in the monitor, I can now implement this thing. So in the monitor, I could even do that. The monitor must get the channel. Tchan int. So in the main program, I must add that. Sure. Something, oh yeah, the client also gets this now. Make that error go away. And now here, I suppose I can do this inside this block, actually. So I can now write to this channel. What's that called? Sorry. Write tchan. Okay. Write tchan true C and pure C. Why is this now complaining? Why IO?
The broadcast is, the channel is IO.
Hang on. No, there's no IO anywhere.
No, but we use the new broadcast channel IO.
No, but I mean, here it gets a, oh, I didn't add that. Oh, no, I did? Oh, sorry. I like this. Okay, and why is it complaining here? Oh, okay, must import that. And I must pass the channel on. Okay, so now the monitor has slightly changed. Now it's much simpler because the shared state is just an int again, tvar of an int. So I check the current number of connections. And if that equals the old number of connections, I just retry, so I wait. But if the number has changed, I return this new number of connections. But before that, I write the new number of connections into this broadcast channel I now have. So the monitor, each time the number of connections changes, writes the new number into this channel. So that's like writing stuff into the channel. And now the only part that's missing is on the client side, on the in the handler, to actually do something with this. So input, I just forever read line and don't do anything with it. And this is now more interesting. So output channel prime, I don't know, it doesn't matter. That will now forever I read from the channel. So the new count. Read tchen true. Second. Must import that as well. And now I can use the right line to say number of clients change to. Why is it complaining? Ugh. Ah, yeah, because of this. Or is there a region IO? I'm not sure. Nope. Okay. Okay. So what has changed now? So earlier, we in the global state, I mean in the server state, we basically remembered handles or ways to talk to each connected client. Each time a new client connected, we updated this list of the connected clients and added it to it, and each time a client disconnected, we removed it again. And then in the monitor, when the length of this list changed, we used the handles we had to send a message to each client. So now we have changed it. So now there's this broadcast channel, and all the monitor does is it writes the updated number of connected clients into this channel, and each of the handlers now has duplicated the channel. So each of them can now read independently from the others, and they now just wait until there's a new number in the channel. So this here will block until the monitor has written a number into the channel, and then it will just pass that on to the client, this string. So hopefully that should work as before. Just a warning. Okay, I don't need socket anymore, it's a good sign. Getting higher level. Okay, so let's run it and see whether it works. Okay, let's start my thing again. Okay. And if I do anything here, nothing happens. I mean, the read line just didn't do anything. Start this one. Okay, so it still seems to work. Right. Let's disconnect that one, and the other two get informed. Okay, and the last one. Okay, and hopefully here, yeah, also no nasty error messages or anything. Okay, so that's that. So using channels, I mean, it's a nice way to communicate between threads. So now we have this, the server basically writes into this broadcast channel when it wants to tell something to each client, but it's not responsible for actually sending it to the clients. So the handler, the individual handlers, each in its own thread for each connected client, will listen to this broadcast channel, and each time there's a new number in it, will take it out and pass it on to the connected client. Right, are there any questions at this point? Yes?
So, do the clients need to subscribe to the channel, or that happens automatically?
Well, I mean, sorry. Here in the handler, we got this channel, This is the broadcast channel, and then we duplicated it so that we are able to read from it, because a broadcast channel is like a special channel where you can't read from, you can only write. But if you duplicate it, then you can read, and then, I mean, not really subscription, I mean, it's pull-based, it's not push-based. So we actively wait here, with this read T channel, we actively wait for something in this channel. So each time and this will block if the channel is empty. So this line here, annoying pop-up. So that line 45 will block as long as the channel is empty. And then if somebody broadcasts something, which in our case this somebody is the monitor thread. So if the monitor thread writes a new number of connected clients into this channel, then this will unblock and get this number out of the channel. And then in the next line it will tell it to the client. And then because of the forever, it will wait again until there's a new number. So it's not, I mean, subscription would basically mean I want you to inform me, but it's, I mean, don't tell us, we tell you, and no, it's, don't tell me, whatever. Don't call us, we'll call you. So it's the other way around. So this waits, this line 45 basically listens on the channel until something's in there, and then it gets it out. It pulls it out, yeah. But because of the dub T channel in line 39, I mean, if it was just, if I didn't do this dub stuff, and if you forget about broadcast channel, if it was just one channel, then you could only take it out once. So if there are several clients connected, then only one of them would get it, the new number. But because each client handler duplicates this channel, all of them can get the same number out. So the monitor writes in whatever 5, now 5 are connected, and all the connected clients in their line 45, I mean, they will get this 5 out of their duplicate of the broadcast channel. Okay? Okay, I think that's that. This is now that, I mean, this is the final version of this example. And now we briefly talk about how that's implemented channels. And then we do a more fun example that's more fun than just giving the number of connected clients. But there won't be anything new anymore, just example. So I did this, all of that. Or maybe one remark in case you read the slides and get confused. It's a bit different to the slides how I implemented it now. In the slides, when we remove a client, we always explicitly close the handle. But I read in the documentation that this accept function we use automatically closes the socket. So therefore, I don't have this H close. So because the slides were made originally when we were using a different network package, which behaved slightly differently. Okay, I think I did all of that more. Okay, here in the slides, it's in 2 steps, the new count and the write, but I think that's okay to do it in the same step as well. I mean, I did it in one atomic block. Okay, and this, as I said, I mean, I think it's quite interesting. But I mean, you don't have to worry. I mean, nobody expects you to implement channels yourself. It's maybe just fun to see how something like that can actually be implemented. And it's, I mean, yesterday I mentioned when we talked about threads that they are extremely lightweight, and that if you want anything more complicated, you are supposed to implement it yourself. Or I mean, not you personally, but library authors. And it's similar with this STM. So the software transactional library follows the same philosophy. It basically provides the basic primitives, these TVARs, and then you can build lots of cool other things on top of that. And the T channels are an example of that. And this is just basically to demonstrate how once you have TVARs, you can implement these T channels. But as I said, the details are not important, so I will go through that relatively quickly, I think, and you don't have to worry about it. It's just to demonstrate that you can build cool abstractions on top of these simpler ones. So a channel is basically just, I mean, first of all, this TVAR list is like a TVAR version of lists. So a T list can either be empty or cons of an element and another T var list, and a T var list is a T var that contains a T list. So it's like a bit, so it's like always wrapped in T vars. And a channel is basically just two pointers to lists. And the idea is a channel is basically a pointer that points to to the read end of the channel and to the write end of the channel. So you will write it's two pointers. I mean, there are elements in this channel. They are basically in this linked list. And then there are two pointers to parts of this linked list. And if you write into the channel, you will use the one pointer. And if you read, you will use the other pointer. So there are diagrams as well. So a new channel will create basically a pointer that points to a whole, to an empty list, and then both read and write will point to that. So the image is you have nothing in the channel, there's a hole where you can write into, and both read pointer and write pointer of the channel point to that hole. Now if you read, you ignore the write pointer. I think I should just show the picture. I mean, this is so this is the situation before. The read pointer points to this one there, the write pointer to the end. The write pointer always points to the end of the channel. And if you now read, you do this. So you read the one and change the pointer so that now it points to the two. So, I mean, read, I mean, the details are really not important. The image is more important. So you have this read pointer and write pointer, and read will get this element out and then point to the next one instead. So the next one that reads will read the two. And write uses the write pointer and not the read pointer. So there the image is this. There's this end, and it will change that and write the new element here, and then the write pointer will point to this new thing. So before this channel end, it was pointing to T0, and now it's pointing to this new element that's been written there. So it's really like, you would do it in C or so if you had actual pointers. So just this. And dub ignores the old read pointer and just creates a new channel. So this is the old channel, and dub again needs to read. The write pointer of the new channel will be the same as the write pointer of the old channel, but the read pointer of the new channel will point to the end of the old channel. So that means the moment you duplicate, you won't be able to read the elements that are already in there. You will only be able to read elements that are written to it now. But because now we have two read pointers, two people can now read the same element. That's why these broadcast channels work. Each handler duplicates it, and then they all can read the element that the monitor wrote into it. And finally, broadcast channel. This was the old new channel, and broadcast channel is different in that the read pointer is just not allowed. So if you try to read, it will just throw an error. And the point is, with the old one like this, if nobody reads from it, because you have this read pointer pointing at the first element, then you can never garbage collect. So if you have a channel and you keep writing, but there's nobody that's reading from it, then you will always keep the whole written elements in memory. And whereas with the broadcast channel, because there is no read pointer, this doesn't happen. So if there is nobody listening to it, then it will just be garbage collected. So in our situation, for example, that's better because we don't know how many clients are connected and they can disappear and so on. Yes, so that's that. As I said, not very important. The takeaway is just that you can use, once you have TVARs, you can use them to build something like this, which is a higher level abstraction on top of TVARs. And as I also said, there are different things. There are also bounded versions and all sorts of stuff. Cool things that you can build on top of TVARs. And I think there are also mvar versions. So instead of tvars, you can also do mvars, and then you get mchans instead of tchans. Okay, are there any questions before we get to the example? Okay. And let me just do some clerical work and copy what we have right now to this chat stuff. So this is empty at the moment. So let me just copy source server chat. And then I must rename it to chat. And in the chat itself, let me copy app counting server to app chat and import chat instead of counting. Okay. And I mean, I do have the ready-made thing there, but I would like to develop it from scratch, so it may go wrong, but I'll do my best. Right. So I mean, you are probably all far too young, but in the old days there was this IRC protocol where people chatted in the early days of the internet. So you could connect to like chat servers and then either talk to all people that were, I mean, send messages to everyone that was connected, or also send private messages to people. And yes, and something like that we want to implement now. So the idea is when a client first connects, he must pick a nickname, and the nickname must not be in use already. Otherwise, the server will keep asking for a name. And once he has chosen a new nickname, he's connected. And then he can either just send arbitrary messages that will be broadcasted to everybody who is connected at the moment. Or there are 3 special commands. He can say /quit to quit. Or he can say /tell and a nickname and a message. And then there's like a DM on Discord or whatever. So it will only send that message to that specific person. Or you can kick, I don't know whether that's also an IRC thing. So if you kick somebody, then he gets disconnected. So that wouldn't be very healthy. Anyway. And then in addition to that, there will be broadcast notifications on connects and disconnects. So if somebody new connects, then everybody will get a message, somebody new connected. If someone disconnects, then everybody will get a message, somebody disconnected. Right. And the idea is we use channels again for the communication, or one channel, one broadcast channel. And so in that regard, it will be, that's why I copied the previous example. And let's do this. Right. And first question is, what is the state in this case? Oh yeah, okay. And the state, if you think about it, should be the connected users rather than nicknames. So you basically just have to know what nicknames are currently in use. And because of this requirement that they should be fresh, I mean, obviously we could use a list of names. Maybe we should, I'm not sure. I mean, it would work, of course. Maybe we just use a list of names. I mean, actually, in my sample implementation, I'm not using a list. I'm using a set. There's a set data type. But maybe, I mean, we talk about that next week, I think. So maybe we just use a list. But of course, if you had like millions or thousands of connected users, a list might be inefficient. But for now, it's fine, I think. OK, then that's basically it. And let's try to implement this. Okay, and I try to somehow keep stuff compiling if possible. Right, so the first thing is, so now our state, I should probably rename it to users. And let me just close everything else. How do I rename function F2? Here. So let's call it users instead. And it starts with no user connected. Right. Now what should be, I mean, the broadcast channel, the messages we had in our previous example were integers, the number of connected users. So now what should be the messages? And of course I could use strings, but I think it's better to use, I mean, here I also could have used strings, and I could have put the string number of connected things changed in there instead. But it's normally a better idea to have like a proper type for that, because then you can pattern match on it easily. So let's think about that first. And let's call it message. So what are the possible messages? So somebody could have connected. Okay, and I think in the example I'm not sure whether it's necessary, but and then I probably shouldn't call it users, I should call it names. All right. Okay, so somebody could have newly connected. Somebody could have disconnected. What else? Then we have these special things. So this tell. So tell. Then we need the who sends the message, for whom is it, and what is the message. So name, and string, the actual message. Of course, name and name are also just strings. This just makes it easier to see what's what. Then we have this kick. So who kicks whom. And then we have the general message. So we could call it, I don't know, message, for example. From whom and what is the actual message. So I think that's all. I don't know whether we ever need to show that, but just in case. Okay, let's see. So the channel will now be not ints anymore, but messages. This tvar int is now a tvar list of names, so that's the state. This stays the same. Let's see. So first of all, we need this right, handle client names channel. Ah, yeah. And this monitor, I think we don't even need that. So I can remove this. So this is good. Right. This is all good. Right, then later I must, so here I must remove a name from the list. But at the moment there is no way for me to, I mean the name is not available. So the trick there is, I will use another tvar for the name, and because for the nickname that the user chooses. But at the beginning there is no name, so I can, for example, instead of type tvar name, I can use a tvar maybe name. So let's just generate one. So name or name var, we just, I don't know, name. So new tvar IO. And at the beginning it will be nothing. And I pass that in here as well. Maybe as the first argument, doesn't matter. So I must change the type here. So I have another tvar, which is of type maybe name. So this I should change anyway to names, and now there's the new one, name. So the idea is of this one is, so this is only, this is local basically to a specific client. So this will be the name that the client picks. But in the beginning of course he first has to pick a name. In the beginning he doesn't have one. Therefore I choose type maybe name. So in the beginning it will be nothing, and once the client has chosen a name, it will be just that name. So here in the finalizer, I must remove that name again if he has picked one. I mean, he could also have disconnected before he ever picked a name. So let's see. Let me change this. Do. Okay, so I check the name. That's a maybe. Retiva name. And if it's nothing, that means the user, the client hasn't changed the name yet. So then I'm done. I don't have to do anything, because then he has also not been added to the list, of course. And if it's just n, then I modify Tiva prime my names. So now I must remove this n from the list of names. So I can do, let me just, because the real estate filter, that would have fit there. Okay. What's the problem there?
Yeah, you have to leave
I have to do that before. Yeah, sorry. I need to do this it's not in scope here. And then I can remove this again as it was before. So it's just this with socket. Sorry. Okay. So again, I mean, when a new client connects, I create this additional Tiva that contains nothing at the beginning, which will hold his nickname once he has chosen one. Then I start my handle client thread. And in this thread, the client may or may not choose a name. So in the finalizer, when the client disconnects, I check whether he has chosen a name. If not, then I don't have to do anything. But if he has chosen a name, I must update the list of connected names by filtering his name out so that he's gone from that list. Okay, so that part looks good already. Now, here, this is now, this becomes more complicated because, I mean, we want to modify the state. This, first of all, is called names now. So there's a gap. And these things, let's just worry about that later. And probably for input we will also need that. Let's worry about it later. Okay, so the first thing is here. I mean, at the beginning, or in the first example, when it was just about the number of connected clients, we knew what we had to do, how to update the state. We had to increment it by 1. So, I mean, once a client has connected, the number of connected clients increases by 1. So we had this +1 there. So now our state is the list of names. So now if a client connects, we want to add his name to the list. But of course, when he connects, he hasn't chosen a name yet. So we must somehow first make him choose a name. And right. So let's do this. Let's call it pick name. And it will need all sorts of arguments, but I don't know which yet. So let's start with IO name. So in the end, the outcome of this will be a name. let's see. So it should probably start by a message from the server to tell the user to please pick a name. So I need a way to communicate with the client. So at least I need this write line as an argument. And then I can start with write line, please choose a nickname. Okay, fine. Now the user can say something. So we also need a read line to see what he says. Let's call it N, whatever. Okay, and now, of course, it must be unique. I mean, I think in my example, I also checked that it's not the empty string or something, but maybe I can not do this now, or is it important? Okay, I mean, fine,
Maybe
I can check.
Someone hits enter without.
Yeah, okay, fine. I can say, so if it's the empty string, if, then I just do pick name again. Or actually, I should, because there will be a lot of parameters and I don't want to repeat them. So the common trick there is that here you write go and then where go to. So I can just say then go. And I don't have to repeat write line and all the other arguments again. So if, or I can also say write line, please don't use the empty or an empty name or the empty name. And I try again. Okay, so now it's not the empty name. The next problem now is that it could be a name that's already been taken. And now we must be really careful. I mean, yeah. I mean, we could, of course, just like read what are the names, check whether it's in there, and if it's not in there, it's fine, and we add it. But I mean, then we have to worry about concurrency, because then in the meantime, so we read what are the names now, and we see his name is new, but concurrently some other client connects and is faster, picks the same name, and then we would end up with two people with the same name. So this should be transactional. This check and adding it. So we do that in STM, in atomical block. And we will return true or false depending on whether that name is okay or not. So atomically do. Okay, so we check the list of names, which we don't have at the moment. So I must add that as an argument. So the TVAR, probably there will be a lot of arguments. TVAR name. Okay, so I will read that. Names. Read TVAR names. I must give it a name, of course, and I also should have given a name to the read line. Names. Okay, now we must check whether it's in there. So if N, LM, NS. So if it is in there, then he can't choose the name and we can return, I mean, stop with pure false. So not good. And else do. So now the name is okay. And now we will, in the same transaction, add it to the list so that nobody else can sneak in and pick the same name. So write or modify TVAR prime names. So we add it. And we could do a pure true. Let me just get the annoying things away. Why is this giving me? Oh, okay. If doesn't need brackets. Okay, so that would be fine. But we also have this name, so we could in the same transaction also actually set the name now. So I can add yet another parameter. I can also pass in this tvar adjust name. Oh yeah, and actually I should, maybe, sorry. Because that also should happen atomically. Because remember in the finalizer, I mean, now we added it to the list of names. So if I did that outside of the transaction, it could happen that the client disconnects when I have just added his name to the list of names, but haven't just updated this one, the one that holds his actual name. And then in the finalizer, we wouldn't remove it again. So it's important that that happens in the same transaction. So we add it there as well. So we also write tvar name just n. So I think this is okay now. So again, so we get as arguments in this pick name helper function a way to communicate with the client. We can write to him and read from him. And we have this tvar that contains the picked name and the tvar that contains all the names already in use. So we tell it to choose a nickname. If it's the empty one, we try again. Yeah, that as well, I think. But okay. I could also say null and.
Yeah, I thought that was the.
Yes, I thought so too. Okay, if it picks the empty name, we just try again. If not, now we check, we compute this B whether the name is already taken. So we look which names are already taken, and if the name is already taken, no, it's the other way around. If the name is okay, so if it's fresh. So if it's already taken, then it's not fresh, we return false. If it's taken, then atomically, I mean, this is all an atomic transaction. We add his chosen name to the list of names. We set his chosen name to just the name, and we say true, it is okay. And now, so if B, then it was okay. Then I can pure n, n, and else I must try again. And maybe I should give a message, so write line, all name already taken, and go. Okay, so this is now that helper function. And that's, I think, the most critical one as far as concurrency is concerned, to get that right, to make sure that we can never end up in a state where we don't, I mean, yeah, we have like two users with the same name, or where we forget to later remove him again when he's disconnected. Okay, so now we can use this. What was write line, read line, maybe name, okay. So here in handle client, so we use this now. Pick name. I probably should have chosen the parameters in the same order as they were here, but never mind. Write line, read line, name names. Okay, so at this point, our user now has n is now a valid name. It has already been added to the list of names. And now we can announce to the world that he has joined. So, and we have the ch one, the broadcast channel, to write to that. So now we can do atomically write tchan ch. And what's the message? Connected n. So, I'm sorry? No. Brain is for reading. Ch is for broadcasting. I could abstract it. I think in the other solution I abstracted that away. Send message and read message. Maybe I should. Oh, maybe, I don't know.
If it gets messy, we have to.
Yes. Right. And did I do the disconnect already in the finalizer? No. that I should also do. So I have the channel here. So instead of just modifying the names, I should also broadcast to the world that he has disconnected. I can do that here. Right. So that's also then atomically right. Tchen. Is that in scope there? Yeah, it is. Disconnected N. Why is that giving me grief? Oh, because this is inside the atomically block. Sorry, I forgot. So I don't need the atomically. I'm in this block here. Right. Okay, so this should actually take care of that. And in principle, we could already try this out now. Maybe we should before we do all the other things. But then I must just, I can't have this. And actually the input, whatever. So I can just do forever get or read line as before and ignore inputs. And output, I can also do, I don't know. I don't need this now. I can just, for the time being, let me just comment this and just do forever read line here. Okay, so I don't really need this channel, but so this should hopefully be okay now that, let's see. Let's just try it out. It's always a good idea to try things out. Chat server. Warnings. Let's see. Okay, let's start one. Okay, please choose a nickname. Let me first try just pressing enter, so that shouldn't work. Please don't use the empty name. Please choose, okay, so far so good. Now let's say Lars. Okay, and nothing happens, but because nobody is doing anything about the messages. But now so it's not very interesting, but if I now couldn't, sorry. That all the okay, now if I start a new one, if I now also pick Lars, then it says name already taken, so that seems to work. Okay, if now, let's see, if now I go back to this one here, Lars, and disconnect, and connect yet another one, then it should be okay to pick Lars again, because that one has, yes, and it works. So that part seems to work. Okay, so far so good. Sorry. Right, so I can stop it again, this and that. Right, so what is missing? Now, of course, the interesting part is missing, that I'm in the messages. So maybe I start, let's see. So let me put this back. And now output, input. So let's first ignore input and start with output. So that's for like passing on the broadcasted messages to the user somehow, or react accordingly. Okay, and it needs this channel to read. Yes, so far so good. So let's try this. Channel prime. And let's also use a go here, because I think there will be more arguments. Okay, and the first thing will be the same. So we need to listen to incoming messages. So message is atomically read tchen ch. Okay, and now of course it depends on the message type. So case message off. And okay, if connected, whatever, M. So if this is us, then probably we don't want a message. I think in the implementation, then the one that just connected doesn't get the message that he just connected. But at the moment we don't know who we are here because this N is not in scope. So I add this here and here. Or maybe I don't know. Yeah, N. So N is me. So let's put a guard there. If the one who has connected is somebody else, then I write, which I now can't because I need to know how. So I need another write line. Or is that in global scope? Oh yeah, that's in global scope. I can. Sorry. So I know how to write. So write line. It's of course now like I think that's that. M. So right now only that is handled, and maybe I can do the disconnect as well. So disconnected M, and there I think I don't have to check if it's myself, because if it's myself then I will never get there because I'm already disconnected. So I can do write line sorry, no guard. My apologies. Okay, maybe we can try it again. I mean, maybe it's a bit tedious to try it so often, but I personally believe one should try or test very often. Otherwise, it's better to catch problems early. Okay, we don't need to retry anymore, but let's see. So now I start this one. Please choose a nickname, Lars. Okay, don't see a message because, I am the only one at the moment. Let's try this one. Please choose a nickname, let's say Robertino. So now, the moment I press enter, Lars should get this message that Robertino connected. Okay, I did, but it ends afterwards. So there's a bug, and I also know what it is. I forgot to call go again. Earlier we had this forever. Now, on purpose, I didn't do this because in certain cases we want to stop, but in this case we want to go on. So I actually need to, I can also use parentheses. I don't know. Or I do. Why not do? And same here. Otherwise it stops, and then this race will make everything stop, and the client disconnects. So same here. Go. Okay, and then I can remove the retry for the time being. Not sure, I think I won't need it. Okay, let's try this again. So good thing I did try it. Okay, so Lars, so far so good. Robertino. Okay, now it didn't crash. So, and now let's maybe take a third one. Carina. So now both Lars and Robertino got the message that Carina connected. And now let's start disconnecting people. So if Robertino disconnects, then Carina and Lars get the message. And if Carina disconnects, I get the message. And of course, if I disconnect, then nobody will care. Okay, right. So that part seems to work with the connection and disconnection. So at the moment, it's complete. I mean, it doesn't matter what. So we have completely ignored what the users type until now. So let's do this now. But the connection, disconnection part seems to work and keeping tracks. I mean, that's actually the critical part, keeping tracks of who's connected and that the nicknames are unique and so on. Okay, let's see. So now we somehow need, I think we need something like and this is actually, I think that's also not in my sample solution. I think it would be a good idea to write a parser basically that takes a string what the user typed and convert it into a message. Does that make sense? Yeah, because everything the user does is yeah, let's do this.
It's a string, but
I mean, everything is a message of the message type. So that might make sense, right? So let's call it parse. It's also a nice preview for tomorrow. Parse message or something. Or pass user input. So if the user now sends a string, we want to turn that into a message so we can better pattern match and so on. And I mean, we were telling you the whole time that if you have a program with I/O, one should try to keep the I/O to a minimum and as much as possible in pure functions. And this is a bad example because everything is like one big I/O mess. But at least something like this I can do purely and then also test purely. So let's see, there were these special cases. Let's look at the slide. Maybe let's start with the easy one with quit. So if it's quit, I mean I can do it like this, then it's just I need
words.
I'm sorry?
Words.
Yeah, but for this one I can just use quit, right?
Right, yes.
But I also need the name, my own name, because the quit message takes as argument, I think, who quits, wasn't it? Let me check the message type. Oh, there is no quit, I forgot that. So where was it in the order? Tell, kick, quick, tell. So I forgot this as a message. Quit. I don't need the name, right? No, I don't need. Okay, fine. Don't need the name. So it's just quit. Okay, then we have this tell. So there we, or actually, I mean, but in that case we have exactly, yeah, okay, we need words. So case. So I mean, a simple dirty way to write this parser is to use this words function which splits the string at spaces into words. And if we have 3 words where the first one is tell and the second one is a name and the third one is a message, then that's tell, but now we need a name, my own name, because that has 2 arguments. So here we don't need this, but here let's call it n, m. So I am telling m the message. So then we have this kick, some name. Sorry, it's a case. So kick, and it's I am kicking M, and in all other cases, it's just message from me S. Okay, I mean we can try this out if we want. So let me do cabal REPL. Pass user input from Lars. If, for example, I say I quit, then it's quit. And if I say tell Robertino, I made a mistake. If I, for example, Karina is late, then it won't work because there are several words now. So I found a bug. Because now it's message, but it should be tell. The reason is it only works if there's exactly one word. No, it's fine. I can just use this. Yeah, unword. There, yeah, that's right. Unwords. So now this should work. So I mean the problem was this only worked if it was one word, if the message was one word. But if the message was more than one word, then it wouldn't work. But now I just check whether it has at least, I mean, starts with tell and then the name and then arbitrarily many words. But now it's a list of words, so with unwords I smash them together to a sentence again. So now this should also work. Quit still works. Okay, now it still not works. Why not? Did I reload? Yeah, I think I did. What did I do wrong? What's words? Tell.
You save the file?
I'm sorry?
Save the file.
Sorry, again?
Save the file.
Oh, thank you. Okay. Yeah, now it works. Kick, let's try the kick. And I think that's it, right? And if it's something arbitrary, okay, good. So now we can beef up this input. And in principle, the input is now we just pass this on and broadcast it, except for quit. For quit is special. So let's see, because we have to stop then. So let's now do this input thing. Sorry, where is it? Here, input raise output. At the moment, we completely ignore this. So let's also beef this up. So first of all, we need the channel because we need to write to something. Okay. And now let me remove this forever and instead write go. So it's another go. Go. So the start is the same. We read a string from the client. So that has nothing to do with TVAR, so it's just read line. So we read the line. And now we pass it with our new function, pass user input. And the name we know, that's this N. At the moment we don't know it, so we pass it into this input as well. Okay, pass user input S off. Right, and now we must see. For example, if it's quit. then we can just stop. So by stopping, we just disconnect, and then it should automatically, everything should work. Okay, what else can it be? It can be this tell. Oh no, let's handle the special cases first. So no, kick is also not special. That happens on the other side, in the output, or can be handled in the output. Tell can also be handled in the output. So everything else can just be broadcasted, I think. So everything else, if it's some message, we can just do atomically write tchen ch the message, and we go again. There we go again. Right. So this won't do much yet, but the quit should work now. So if I try it again, because in the output in the case it's not connected or disconnected, it won't do anything. But we can try it at this point. What was the warning?
I think CH is shadow, the lower.
Yes, in line 61. So I don't need it because I already have it. It was a parameter to the right. Okay, good point. So let's see. Let's connect 2 people only. So if we switch to, or if Robertino, if he now types something, nothing should happen at the moment. But if he types quit, he has disconnected, and also I got the message that he disconnected. So I didn't have to do anything specific. I just make his handler stop, and then what we have done so far already, the finalizer takes care that this is taken, that the accounting, the bookkeeping works. So that works nicely. Right, and now the interesting things. So everything else should now is, I think, only a matter of this output function that we do it there. Because at the moment in the output, we only react to connected and disconnected messages, but not the others. So now we can, the order doesn't matter. So for example, I don't know, tell. So if it's tell,
Excuse me?
yes?
I have a question. Can you just go back to the previous slide?
Slide.
Yes. Where you connected Robertino, and then there is the string of letters that you also connected, but it is not listed. So why wasn't it listed as a name?
You mean here when user input is handled by this input function we wrote. This one. So this S was, it was read, this weird string of letters was read. Then it was parsed with our parse function. And because it's none of the special cases, it was just passed as a message. Okay, so far. Then, and then it was broadcasted. But we don't do it, so it's here, we pick it up, but it was message something. And at the moment we're only handling connected and disconnected, and in all other cases we didn't do anything. So I can change that now actually. So if I handle this now, and then we can do it again, and then so somebody sent a message, and if it's not from us, then we can say write line. So let me do this again. So this one connects, Lars, and this one connects, Robertino. And if I now do whatever, now, because I'm reacting on this message type now, the message type, now I get this effect. Earlier I was just ignoring it, I wasn't doing anything with it. I mean, people were receiving it, but I didn't do anything with it. Now I'm writing it to the client. So now, get that. Yeah, welcome. Quit. And actually, maybe we should have another break at some point, not sure.
We're almost finished.
Yeah, I know. But I thought that we should leave something for, but we can also, I mean, because Karina might have a way for us to actually try it, like.
Oh, right, okay.
So I don't know.
10 minutes?
Yeah, let's have 10 minutes break. I mean, this already works, and it's not much left. But maybe there's a chance to actually demo it with several machines. We were just struggling earlier with firewalls and stuff. But in principle, it doesn't have to be just on my machine, of course. It's a server. So maybe we can demo it. So let's have another short break, and then we do the rest. There's very little left. That's the
Question.
That's all. Okay. Okay.
Maybe you could try to implement the key.
Okay, almost done. Right. So what's missing is the tell and the kick. So let's do the tell first. So tell whom message. So this should only be displayed as if this client is the one for whom the message is. So whom equals n. And also, I mean, I think we didn't check that, but who should be somebody else, I suppose. I mean, we could have done that in the past as well, but we didn't. So let's do it here. So whatever. Who. Some other symbols, I don't know what was used there.
One DM.
I'm sorry, which one?
One a D and an M.
Oh,
Direct
DM?
message. Yeah. I don't know. I think it was the same symbol.
Okay, so can try this. And the
Go.
oh, the go, that's right. The go. So let's try this again. Class. No. So, okay, let's say Karina. If Karina now says tell Robertino, class is stupid, then it doesn't work. So, oh, Roberino.
Yeah.
And there is no Roberino, so it didn't tell anyone. Robertino, class is stupid. Right, then he gets it, but I don't. Okay. And now the final fun is kick. Whom? So this is only relevant if it's us that get kicked. Whom? Maybe I should also check that the who is not me. Or maybe I could kick myself, I don't know.
Yeah,
but
it's the same as
then I
quit,
can,
so
I'm sorry?
same as quit.
It's
So
same as quit, yeah. Okay, so in this case, I know what I don't need to do, because in this case I will stop, I will quit. So I just say write line who kicked you. And nothing. So no go. So we will, and that's it, I think. So let's try it. So, us, Robertino, Karina, hello everyone. Okay, and now kick Robertino. Okay, so Robertino gets the message Lars kicked you, and his session stops. And yeah, we get the message Robertino disconnected, but we are still on. So that's it, basically. So now, good. Okay, I think that's it. So this is what we wanted to implement for this server. Are there any questions? So it's just a hopefully fun example of what we have learned yesterday. How to, and with these channels now, how to implement something like that. So something non-trivial that could actually be used. So as I said, before your grandfathers were born, there was this IRC protocol on the internet that was similar to this, I think. I'm not sure about the kick, whether it had kick. And I think it had some extra functionality like file transfer and stuff. But in principle, people were using stuff like this to chat. Maybe some, I mean, of course, one could also, if you want to, one could extend it. I mean, I suppose one could have, for example, something like /list that gives you all the connected user names or something, because you might have missed the announcement. Or I mean, if you joined afterwards, then
you get a list of everyone.
Yeah, or one could present a welcome. These are connected or whatever. I mean, there are lots of things one could improve. But in principle, it works. Of course, it doesn't remember anything, so there's no chat history. But I mean, one could do all these things if one wanted to. Okay, so I think that's it for today. So today we were very fast. I hope we don't now have to wait for hours for food. But
any questions?
Yeah, I mean, of course, if you have any questions to anything, we can also use the time to answer those or do more examples with whatever.
Questions not only about this, about like
anything,
assignments, curiosity.
I mean, for example, I have this example about the list monad with send more money that I can do.
Yes.
Or I could, yeah. I'm not sure, should I do that? Maybe. That's always actually a nice example.
Yeah, one more example from Monas, it never hurts.
Right. So let's, I mean, if no one has a question, then we can do one monad example with lists, because that's quite unusual with this indeterminism. Yeah. I mean, the last example we had was, I mean, they didn't really fit this metaphor with indeterminism because it was counting words in a sentence, so there was nothing indeterminate. But to actually show you that, like a very simple form of logic programming, what you would normally do in Prolog or something like that, you can just do in the list monad, and it's quite cool, actually. Right, let me try this. It should, of course, not be in here, but let's put it in here anyway. So I just add but maybe not servers, I just call it, I don't know, list. Okay. In source. Right. Okay. Right. Let me just think how that works. Okay. So the idea is, I mean, there are these puzzles, I mean, this type of puzzle, I'm not sure what it's called, where each symbol or each letter corresponds to a digit and different symbols to different digits, and then it has to somehow add up. And the one I sometimes amuse myself if I don't have anything, no phone, no laptop, just a piece of paper, is the send more money. So some of the story is that some rich son gets sent away by his parents and runs out of money and then sends a postcard to his parents, send more money, and the sum is basically encoded in this. So it looks like this. And we have send, send more money. So the idea is that I mean, each letter corresponds to a digit, and I mean, S and M must not be 0. So I mean, the sum and different letters, different digits, and the sum should add up, and S and M should not be 0. So I mean, it should be like a proper sum. You wouldn't have a leading 0. And I mean, in principle, of course, there might be no solution or several solutions, but it turns out that this specific puzzle has exactly one solution. And so the puzzle is to figure that out. And I think when I did that in Mongolia, then Sengun, one of our colleagues, figured it out before I could write the program by hand, of course. But yeah, normally it's, I mean, if I do it by hand, it takes me an hour or so, I don't know, or maybe half an hour. But it's not too easy. But it's doable without actually trying stuff. So basically, you can just, using logical thinking, figure it out. But in using the list monad, it's simple, or not simple, but doable. Right. And let's try this. And I think a helper function is useful. Let's call it draw. So the idea is I have a list, and it gives me all possible ways to pick one element from the list, and then it gives me that element and the remaining elements. I think that's a useful helper function. So let's try to implement this. This is also a good exercise, would be a good exercise, but I'm doing it now. So standard list pattern. So if I have the empty list, then the result is just the empty list. There's no way. And if I have a non-empty list, so what can I do? So one option is to pick the x, and then the remaining elements are, of course, the xs's. So that's one option. But alternatively, I can also recursively draw from the x's. But then, if I do this, then I must not forget the x. So the x is then, so I can, for example, use list comprehension. We haven't seen an example yet. So let's say I recursively draw from the tail. But then it's y, but I mustn't forget the x. And why is this not working? Because I didn't call anything. Recursively draw from the axis. Right. Let's see. Things like that is always good to try that out. It's a pure function, so now this has nothing to do with I/O anymore. It's just pure Haskell. So let's say draw 1, 2, 3, 4, 5. So I can pick 1 and 2, 3, 4, 5 are left, or I can pick 2, then 1, 3, 4, 5 are left, 3, and so on until 5 and 1, 2, 3, 4 are left. Right. And I think this is the useful one you need. And the idea is that, okay, so now solve, or I can call it send more money or whatever. So send more money. Let's see whether I get that right. So it should be, okay, and of course the result type, okay, how do we represent the result? I mean, we could of course just use a very long tuple, but maybe it's better to define a type for this. So solution, so what do we have? We have the S, Let's just use ints. E, N, D, M, O, R, then E again, which we already had, then money, M, O, N, E, and Y is. I think that's all, right? And now? Yes. Okay. So I want the list of all possible solutions. And the idea is that I pick just in the list. So list monad is indeterminism. So I basically just pick the numbers one after the other and in the list monad. So let's start do. Let's just, not think about it and just start with the first one. So I pick the S. So S and whatever X as 1, there will be draw. And here I have all digits available except because the S is the first one, it can't be a 0. So I must, okay, must just think of the 0. Or I should start with a different one. Sorry, I shouldn't start with the S anyway. I should start with D, E, and Y. Right. So sorry. Let's just start the sum here. So I start like indeterministically choosing the D and the E. So let's do this. So I choose the D, and that can be any digit. So now the E can be any. So now, this is now. You can think of it as like you can think of it as an oracle or something. The draw somehow knows the solution. It's an indeterministic computation. So, in fact, it's just the list of all possibilities. But you can think of it that some oracle gives you the right one now. Okay. Now the E. It mustn't be because different letters correspond to different numbers. I don't draw from everything, but only from X as 1, from the remaining digits. Now the Y is determined because it must be the sum. So, and I have some carry. So let's, how do I do that? There is this diff mod, hang on. There is diff mod. So if I do diff mod 1310, I get 1 and 3. So that's a way to split it into digits, a 2-digit number. So let's call it carry 1 and Y. Diff mod D plus E. So because Y needs to be D plus E, but there can be a carry. Sorry, 10 of course. So D plus E is the sum, and now modulo 10. So Y is the remainder, and C1 is the carry. That can be 1 or 0. Right. I have that. Now let's see. Now I can draw the N and the R. So as X as 3. It would be better, I think, to use the state monad or something. The R, sorry. I hope I get this right now. Let's see. I mean, this looks like state monad already because I have as state the remaining ones. So probably I should do this, but so maybe it's a bit early to do this. Maybe we can revisit it once we have talked about monad transformers, and then it's much simpler. Right. Yes, I didn't think of that. But I think it's still doable like this, I hope. Okay, so now we have the R. And, oh yeah, one thing I forgot. I mean, all the letters have to be distinct. So the D and the E are distinct by this construction because we pick the E only from the remaining ones. But the Y we didn't check that the Y is it's not the same. So we can use a when here at this point. So we should check as early as possible to cut it off if something is wrong as early as possible. So when Y equals D or Y equals E, we fail with the empty list.
Yeah, and it's E. You put the same equality comparison.
Yes, D and E.
Yeah, that's it. We don't give
That's right, right?
anything.
Is that right so far? Yes. Okay, NR. So this basically, I mean, this may look weird. This is basically throwing an exception in the list monad. So by giving the empty list, it means there is no, I mean, there is no way to continue. There is no solution. And that means, if you think about it, how bind in the list monad works, once I have empty list, then nothing else, everything is cut off. So this basically means if Y equals D or Y equals E, then it fails. So then it will try a different choice for D and E. So okay, now I have N and R, and of course they must also be, so N, I mean it's always unequal to D and E, but maybe this is bad to do it like that. Sorry, because then I have thousands of these conditions. Let me rewrite this. Let me draw the Y as well, like this. Sorry. I mean, it's correct. But now I have to compare every new one with Y. So I think it's better to draw the Y. Yes, that's better. To draw it. And now put a check in. And I actually can do the check. Sorry. It's another helper function that I can put here. Check. Bool list, list of unit. So check true is unit and check false is the empty list. Right. Oh, that's like guard basically, right? I hope this will work. Let's see. Okay, so at this point now I can check that I can compute this C1. That's the carry. So I want to use this condition now. So let's just first explicitly. So check that Y equals D plus E mod 10, and let C1 gleich D plus E diff 10. Okay, so this is this. Right. Now I must be careful because now I did it differently. So I draw this is now 4 already, 3 and 5 from 4. Okay, NR, where are we? NR, now E we already have. So this is, I don't have to draw the E, so I can do another check. That N plus R plus the carry must be E. So check n, E equals n plus R plus the first carry I had. Mod 10. Okay, and now I have a second carry. C2 is n plus R plus C1 diff 10. Okay, now I'm here. Maybe I should somehow comment this, or what have I drawn now? I have DE 1, 2, 3, 4, 5. Let me just return those 5 just to see whether it works in principle. So int, and let me comment this and just return a pure, what was it, what was the DEY NR. Okay, let me just see whether to this point it works. Probably that's now a very long list. So let's first ask for the length. Oh, no, not that bad. So, I mean, let's just check whether that works until now, or whether I made a mistake. So, for example, the first one says, maybe we should. So we have, what was it? Send plus more money. What's the first solution? 1, 3, 4. 1. Oh, that looks good. 0, 2. And that something's wrong already? Yes, because this doesn't add up. So I made a mistake. Let's see. Let's just check in this first case. So 1, 3, D and E is 1 and 3. So the sum is 4. That's the Y. So that so far so good. And now the carry should be 0, right? The C1 should be 0. D plus E is 0 in this case. I mean, D plus E is 4 divided by 10 is 0.
Yes, it should.
Ah.
Yes, it runs to 0.
And now E equals N plus 3 and 4. How irritating.
Maybe you have to add parentheses in the sum, just in case you want it more separate.
Oh, right. That could be it. Yes, I think that's it, actually. I hope that's it. Let's hope it is this. Okay, better, I think. Okay, 1, 2, 3, 4, 8. 1, 2, 3. Yes, that's better. 8, because now the sum is 12. So we get a 2 here, and this must be the same because E. So I think that was it. Thank you. Okay, right. Now I think it's almost a pattern already. So hopefully now the rest is. So let's see. So where are we? So we had the NRE now. So now the E we already have, so we have to draw the O, and then we can check again. O, so draw axis 6, draw axis 5, and now we must check the next sum. So we must check that E plus O equals N. So check and the next carry okay. Let's just try it again. Just to be safe. Okay. So now the first. 1, 2, 3, 7, 5, 4. 1, 2, 3, 7, 5. So this adds up to 12, and we have 1. And now 4. Oh, the E is 2. So the O is 4. Right, and this also adds up. So this is 7, and this must be, that's the N, that's the check. So far so good. Almost there. Right, what next? So now we have the E plus O equals N. So we had that now. So we have to draw the S and the M, and then that should be it. So S and M. And we can immediately check the S must not be 0. The M must also not be 0. And now the final thing we need to check is that this sum here is right. That S plus M plus the carry is 10 times M plus O. Of course, we could do that in the same check. So what did I say? S plus M plus the carry, the last carry, C3, is the same with 10 times M plus O. And now we can actually, we have everything. We don't need this anymore. We draw Y somewhere?
Yeah, the
Oh yeah,
beginning.
yeah. What is now missing? Ah, okay. All right. So if all went well, then we should get exactly one solution. Let's first, yeah. Okay, so what is it? Can you say maybe like this, send more money? So S?
9, E 5, E equals 5, N equals 6, D equals 7, M equals 1, O equals 0, R equals 8, and Y equals 2. 2. Right.
2. So 7 plus 5 is 12, carry,
Y, okay. Yeah.
carry 1, 9, 15. So that's the E. And 1 carry, 6, which is this N, and 10. Right, and I think all the ones are distinct, and the sum is right, and I think it's good. Yes, so you can do fun stuff like that in the list monad. But as we saw with the stupid XS 1, 2, 3, 4, 5, 6, 7, that screams for state monad somehow. So once we know about monad transformers and know how to combine the list effect with the state effect, then we could do that much cleaner, where we don't have to explicitly carry the remaining digits around. So we could put them in the state. But nevertheless, I think that's fun. So it's a bit like prolog programming, basically. So this draw is like you indeterministically choose, and then this check. So I mean, if you could, of course, do all the checks in the end. I mean, I could just draw all 9 or 10 letters, and then in the end check that the sum is right. But then it would be very inefficient, because then it would have, whatever, 10 to the 10 or 10 factorial long list, and would check all of them. So by adding the checks as early as possible, it cuts a lot of the search tree out, and it's, as you can see, very fast that it generates the solution. So I think that's a fun application of the list monad. And there are I mean, you can do that. I mean, one could also use that to solve Sudokus or all types of these puzzles. There's one problem if you have like a search tree, and with the list monad it's left biased, I think, so it always tries the first, and if you have like an infinite branch, then it will never even get to the other branches. And there are other monads on Haskell, I forgot, I think logic T or something it's called. If you look on Hackage, I think it's logic T. Right. So this is then the real thing. Sorry, it's loading. Right, and there basically you have it properly. And there this problem disappears with the, right, and it's a logic and, sorry, it's a monad somewhere, it will say. So it's this logic monad. So there's a monad somewhere. But in principle, it's like this list monad. It just fixes. So like if something is infinite, it makes it fairer. Yeah. So you can solve puzzles like that with this. So you just, I mean, it gives you indeterminism, and then you can just basically try all the things at the same time, sort of. Of course, in practice, it tries them one after the other. Yes. But I think Zengun was faster. And maybe we can revisit it after we talked about monad transformers to see that then you can do this much more concise. Okay, any questions?
Can you like add more rules like on monad, like to make it like,
Sorry, can I do what?
Can you add more rules like the thing you're implementing like a monad, like let's say instead of a list you have like a probability distribution.
add more rules.
Yeah, like the data structure you're making. Like, what I'm trying to ask is, like in this draw function, right? If you draw it from like a probability distribution,
Oh,
yeah, so how that works?
probability distribution you can also do with list monad basically. So I mean, yeah, we could also do a fun example there, but maybe some other time. I'm sorry, yeah, with Monty Hall, or should we do that now? I don't know.
Or will we have it in a lesson already? I think. Or in
No,
or in a
it's not an assignment.
not an assignment.
No. The only problem is that it's not clear that it's a monad maybe, but maybe they would believe me.
You have to trust.
I mean, if you still have time, then I can do that. I'm not sure. Don't have to. Is the food already here?
Yes, it's here.
Okay, then we should stop, I think. But that's one of my favorite topics, so probability monads. So we don't have to do it now, but it's a fun example, so maybe if tomorrow we have time, we can do it. So if you don't just take list of A, but if you take list of A, doubles, for example, then that can represent, and if you have like the invariant, that all the doubles in the list must add up to 1 and be between 0 and 1, then you can consider that as a probability distribution. And that is actually also monad. So return or a pure would be the one element with A, 1, and then basically the bind follows this law for, whatever it's called, it's the probability rules. So it's relative probabilities. And then you can do probabilistic computations in that monad. And so you can solve like probability problems. And in the end, you get the distribution of the result, like the proper distribution. And if you don't use double but rational, then you even get it precisely. So you can basically get precise, discrete distribution, probability distributions. That's also monads, one of my favorite monads. And there are also fun examples to do this. Right, yes, that's similar. So you can like beef the list monad up to have like probabilities. Okay. Are there any other questions? Okay. Okay, then maybe we should stop for today. Okay, thank you very much.